University, and he's going to tell us about spectrum of tightly knotted flux tubes in QCD.
Yeah, so I want to talk a bit about basically what we've been doing here for the last 4 months. And that's tightly knotted flux tubes. And
Your microphone doesn't seem to be doing anything.
Green light.
Red light.
At the top.
Try to push.
Push the top.
Good.
How about that? Okay,
Close
good.
the light.
Move it out.
Okay, better?
Yeah.
Okay, thank you. So there's many systems that potentially can be tightly knotted or tightly knotted, and there's examples from many areas of physics. Classical examples are plasma physics, but also in biology, DNA can be knotted, and even there are macrobiological systems that can be knotted. There's actually an eel that can tie itself in knots.
Elephant's trunk.
Pardon?
An elephant's trunk.
I forgot about that. That's another example. The quantum systems that we're interested in are QCD flux tubes, but there are also a plethora of other flux tubes in physics, quantum flux tubes, like superconductors have flux tubes, and then superfluids, atomic condensates, and so forth have vortex lines, and even perhaps cosmic strings can be knotted. And in the quantum case, we've argued that there's a universality for the tight knot case. Well, probably the best known classical system is plasma physics, where you can have linked and knotted fields. And well, Keith was one of the people that spearheaded understanding this stuff. The tight knot cases correspond to Taylor states in some cases. This differs from QCD in that we're going to be dealing with tubes of fixed radius. So that's the quantum case. And as Lou mentioned, Kelvin considered, well, he made a model of elementary atoms as knotted fluid vortices in the ether. So I think he's probably the first one to make a careful consideration of the spectrum of knots and think about elementary particles. In our case, actually it's a little simpler. So we're going to consider the tight knot spectrum in QCD, and we'll call these particles glue balls, but it's a whole spectrum of states. Flux is quantized, the radius of the tubes are fixed, and the energy of the state is proportional to the length with which you tie the knot. This is a semi-classical model, so it's on the order of, say, the liquid drop model of the nucleus or the QCD bag model. So it's not a full quantum model, but one could try to turn it into one. So in QCD, we have confinement. That's what confines the flux to the tubes. And at long length scale, things get confined. The typical energy scale in the problem is about a GeV. So quarks and gluons and flux in QCD is confined to either bags or tubes. And we're interested in the tubes. And it's chromoelectric flux. So if I take a quark-antiquark pair, pull them apart, I get a chromoelectric flux tube, not a magnetic flux tube. And in our case, these are going to be closed. So we'll pull it apart and then, say, annihilate the QQ bar pair. So I get a circle that way, but I could tie it in a knot and then annihilate them. I get a knot, or I could make links, and so forth. So here's, again, a picture from either Eric Rodden or Jason Cantarella of a tight knot. After you've got a knot and you let it contract and relax. About the counting of knots, if you look at the crossing number and then compare that to the number of knots you have, you notice that for the crossing number growing linearly, the number of knots grows at least exponentially. So and it turns out that the length of a tight knot is roughly proportional to the crossing number. That means that the number of knots at a given length gets dense as you increase the length. And this is just the prime knots. There's other knots too, like composite knots that aren't even added in here. So we're going to consider all types of knots because physics shouldn't care whether you're a prime knot or a composite knot or a link or a composite link. We just take them all. And so what we're interested in is this case. But these are non-QQ bar bosonic particles. So they're not your standard meson like a kaon or a pion. So there's three types that have been identified. Hybrids where you have QQ bar and a gluon stuck together. You could have, say, 4 quark states. Those are called exotics. The former are called hybrids. And glue balls are states with no valence quarks at all. And their quantum numbers, angular momentum, parity, and charge conservation are 0 plus plus, 0 plus plus, 1 plus plus, and so forth. So it's this collection of states in the particle data table that we're interested in. These are hadrons. They have strong interactions. They don't decay directly to photons. And as I said, no valence quarks. They decay either by string breaking. If I have a knot and I break the string, it just falls apart. It could reconnect, so I could have, say, a link, and I could reconnect, get an unknot, and that would disappear. Or if I have a link, one can tunnel off the other, and the individual loops would disappear. So if you have knotting or linking, you have some sort of topological quantum number. If there's no topological quantum number, there's nothing to stabilize the object. So anything that's an unknot, we assume decays. So there's this summary of assumptions in the model. We're making a one-to-one correspondence between the F states and the knots and links. 1 flux quantum per tube. And the knots and links are stabilized by their topological quantum numbers. The tubes are diameter on the order of 1/10 of a Fermi. That agrees with lattice calculations. It's a detail I'm not going to go into. Any J greater than 1 is assumed to be an intrinsic angular momentum, not a rotational angular momentum for technical reasons. And finally, if we form a knot, it contracts into we assume that it contracts to a tight state faster than it decays. That will allow us to get a measured mass for the object. So here's the tube radius corresponds to a tension on the order of a string tension on the order of a few hundred MeV, which agrees with lattice calculations. And so we make the identification of the lightest F state with the shortest either knot or link. And in this case, it's a Hopf link. The next guy, which is the F knot 980, we identify with a trefoil and so forth. So we just make a one-to-one match and fit the data with knot lengths compared to energies. So Roman and I wrote a paper about the model about 10 years ago, and shortly thereafter we joined forces with Eric Rodden and Jason Cantarella to get a list of the actual lengths of these knots and links, which were not much was known about them at the time, and we're just now about to release a preprint with a reanalysis of all the data. So that's this new fit. Here's some of the this is some of the knot lengths that they get. They get knot lengths to like 4-place accuracy. Not legible from the back anyway, so I'll just skip past it. So what we're doing here is we're fitting a sporadic set of numbers, which is the knot lengths, with a sporadic set of particle physics data, which are the masses of these F states. So they both look rather sporadic. And we look at a one-parameter fit. We also compare it with a two-parameter fit. So if we just fit the uncorrected lengths, and I'll mention how we correct them in a moment, we get a decent fit, but there are some highly constraining states that are pretty far off the line. But after a little thought, you realize that if you have a flux tube and you bend it, the flux, which was uniform across the straight tube, is no longer uniform across the bent tube. It gives you an energy correction, and you can do a little variational calculation to show that the magnetic, well, this is a magnetic case, but we're talking about chromoelectric. So the field will fall like one on radius as you go, radius of curvature of the tube, and you get an energy function that looks like this, where this is the inner and outer radius if you look at a solenoid, a circular solenoid, where that is what you compare with the straight energy functional. And here's the correction. So depending on how tight the bend is, the correction gets larger. And these knots and links are bending all over the place, so you have to add it up section by section to find out what the total correction is. And here is a histogram of the states, or the knots and links that we've looked at. It's the first 72, I believe. Most of the corrections are on the order of 8.5%, but there's some scatter in the data, and that's what'll shuffle these states in our fit once we redo it. Here's the first 950, and you can see again that now the peak is sharper, around 8.5%. So here's with curvature corrections. So, excuse me, we're making a linear fit, but we're allowing gaps. So we may not identify all the F states with a knot or link. And this sort of summarizes the fit. So we look at uncorrected case. It's not a very good one-parameter fit. Curvature corrected gives a very good fit. And then there are two options. We can either fit one of the states and identify it with a longer knot or link or a shorter knot and link. And this case, we'll find that there's a new prediction for a low mass state. The two-parameter fit in the curvature corrected case doesn't improve things, so it's easier, or it's better to go with a single parameter fit. And here, once we do that, you notice that these bad guys are on the line. With the high fit, which we fit this to one of the higher knots or links, there was some tension in the data that allows us to identify, well, we may be able to identify the state that may appear at 1220. It's not verified yet, but there was some measurements around here that showed a possible state. We could identify that with the 421 link at 1190 MeV. So here's, again, the picture of the fit, and there's that new state appearing. So the rest of these are fit. Then the glue ball data gets sparse as we go up near the top here. So there are unidentified knots and links, so those are predictions. So we get one low mass prediction and then lots of high mass predictions. I'm going the wrong way. So that's the new low guy. And these are the states that were out of line that have come onto line. So here's a two-parameter fit if we use the uncorrected lengths. That does bring these guys that were out of line back onto line a bit, but at the cost of an intercept that's rather large. So that's not very nice for the model, so we'd like to do without that. And so that suggests that the curvature corrected fits are the better ones, and we go with those and not the uncorrected fits. So the fit with 2 parameters is virtually unchanged for the curvature corrected lengths. So here's the 2 parameter fit. In that case, notice these guys stay on line. The intercept is consistent with 0. That means the mass per unit length of the tube doesn't have some offset at the bottom, which would be unphysical. And that's just a summary of these points. So we've done the curvature corrections, but there's other possible corrections. So if I have a flux tube and I've got another flux tube wrapping around it, it will constrict it. And if it constricts it, it changes the energy a bit. So that's something else we need to worry about. We don't know how to do that correction for knots in general, but we can do that for a couple examples and estimate what the corrections would be. There's also distortion in the cross-section. So far we've been talking only about circular cross-section, but for instance, if I take a rope and wrap it around a post and pull on it, it distorts the rope from a circular cross-section. So that's another thing that we'd have to take care of. So we've assumed that all these corrections, if you put them together, they're on order of about 3%. There could also be some QCD effects due to confinement that we haven't taken fully into account. But the important thing is it's only the spread in corrections that matter, right? If all the corrections were 10%, then it wouldn't shift anything but the slope parameter. So to move the points around, the individual knots have to be corrected differently. So here's the other possibility where we fit this F naught 1370 with one of the lower knots. So it used to be up here, now it's moved down here. It's still consistent. It's only 1 sigma offline. And in fact, it turns out to be a better fit. And we then fit the first 12 knots and links with the first 12 F sub j states, 1-to-1, with a single parameter. So there's only one parameter in this model. Here's the same thing with a 2-parameter fit, and it's virtually unchanged as it was for the high fit. Here are the predictions. They're all up here. And here's the combination of data and prediction. So 1-to-1 up to this point, and then a few more data points are known, and then we run out of data, but there's lots more knots and links. We run out of particle physics data. There's a chi-squared of 28 for about, I think there's 15 points that we fit. The slope is 65 MeV, and no new states below about 1700 MeV. And this just summarizes that. I think I'm out of time. 1 minute. Well, we've done some other quality of fit checks. We've looked at p-values. Those are all quite good. We've done like a dozen of them. And well, here's the table that we get from that last fit. Here's the F sub j states, the curvature corrected lengths, and the predicted, well, the fitted masses. And then below here we have knots and links that don't have a corresponding F sub j state. So those are things for experimenters to look for. And let me just conclude with the fact that we now have some new predictions for QCD. Thank you.
Question on the back.
I would like to ask, because if I look for particle data group, it seems to me that all the states that you discuss are well-known isoscalar mesons, and I do not understand how you can justify this to be in any way consistent with the QCD.
Sorry, don't understand what?
I do not understand how you can claim your fits to have anything to do with the group global spectrum because all the states that you discussed, except maybe
Well, but many of them have been discussed as glue balls. I mean, the 1500, the
that is-
1710, even the 980.
Yeah, but that is 0 plus plus, F0 1500.
Right.
All the others are isoscalar measures that fit perfectly well with the SU3 quark model.
Well,
And I do not understand if you talk about knots, how can you only talk about the parity even states? Because a knot can twist left and it can twist right. And if you take a linear combination, you have a scalar and pseudoscalar. So I do not see any relation to QCD.
right, but you could have left plus right or left minus right. One would have a quantum, topological quantum number, one wouldn't. And so only one would be stable.
Well, if you take a 0 plus plus state and you say that it's either left chiral or right chiral, you take a linear combination, you get 0 plus minus. You get the pseudoscalar.
Well, you could get,
Because if you take a unknot, twist it left or twist it right, take a linear combination, one is scalar, one is a pseudoscalar. The one with plus is, so you should also have a 0 minus plus.
right, but we only identify, for instance, the trefoil with one of those linear combinations, which would be the plus-plus combination.
Well, the trefoil can be either left-handed or right-handed, so there should be a scalar and,
Well, let me take the plus-plus linear combination.
and it is quark model gives predictions where F00 fit F0 1500 fits the fits a global interpretation, and then the remaining states have well computed the masses.
No, I'm sorry, I missed the last.
I mean, lattice models have computed the global masses, and they're very different from what you say.
Well, yeah, well, I can give you an argument why the glue ball on the lattice should be much higher than these.
But I mean, this F0, yeah, because the mass of quark is finite, and this F0 500 is the linear sigma model meson.
What, the F naught 500?
F0 500 is the linear sigma model meson.
Well, the sigma particle, you're saying.
Yeah,
Well, but we're identifying it with the Hopf length.
yeah, but it has a quark content.
Say again?
But that is not consistent with its branching ratios. It is an SU. It fits an SU3.
Well, it's an interpretation.
Scalar meson.
This is, it's an interpretation.
Yeah. Well, it is an
Why don't we
experimental
give other
verification.
people ask a question,
I
a chance?
put down
I'm
that.
sorry, I already gave you so much time. Renzo.
I'm curious to know, is any role for tight knot, for the tight unknot? Can be a reference for something?
Well, it won't be stable in our case. It would, it would be very light but unstable and dissipate because there's no topology to support it.
How long would one of these knots last? What's its lifetime?
Well, their decay widths are tens of MeV typically, or hundreds. So, 10 to the minus 20 seconds, 10 to the minus 21. They go fast.
I was wondering if there was any possibility of experimentally observing something about how they would interact with one another.
Well, you could, but it would take, some very well-arranged scattering process probably. Well, you could look at decay chains to see how one would change to the next.
Yeah.
You can't produce them and then collide them.
Right.
Another question on the back.
Yeah, in your plots of the fit, it looked like the Hupflink one was well below the line. Why?
That's right, yeah. Well, there could be some mixing with states with valence quarks, as the gentleman in the back was mentioning. There could be other states in the game that could change the overall mass that you would find for these objects. Or
Any other questions? Well, let's thank, one left.
Do you plan to extend this model to mesons and baryons?
well, I'm not sure how to do that, right? You've already got the bag model, which is fairly consistent with those.
That's got nothing to do with tight knots or links.
Well, yeah, you could maybe tie a knot and throw some quarks in the bag, but then we haven't done it. So one could think about it, but I'm not quite sure exactly what to try.
Okay, let's thank Tom again.